So now we move into Module 6, and we're going to talk about operations on functions. And this function notation is really telling us what it wants us to do. In a sense of the way we write something, we have f plus g of x, which is telling us to basically take and add the function f of x to the function g of x. Subtraction would be f minus g of x, which is telling us f of x minus g of x. Here we have f times g of x, so it would be f of x times g of x. And then here we have the quotient, so we have f divided by g of x, so you have f of x divided by g of x. And of course they tell you g of x cannot be 0, because that would of course give us a 0 in the denominator, which is not possible because that would be considered undefined. And they have given us some examples over here where we have f of x is 3x, g of x is 2x minus 4. So here they're just telling us to add those two together. This one they said to subtract, so we take f of x subtracting g of x, and when you do that, you're subtracting the whole thing. Often forgotten about is we distribute that negative sign. And that's how they came up with x plus 4. Then for multiplication, in this case, we did have to do that distributive property. And then for division, we actually, when they divided 3 of x by 2x minus 4, there's nothing more that can be done there. It's just written in the division form because they're both prime in our cases. I mean, we can take a little bit more out of here, so it's not prime. We could factor 2 out of there, but it wouldn't do us any good. It would not affect the overall value, wouldn't change anything. Now, add and subtracting fractions again. The notation for adding is f plus g of x. So we take f of x and we add g of x to it. Simply the entire f of x, and in this case, plus g of x, which is 2x squared minus 5. We add them together. You combine like terms. We have our 2x squared minus x squared, so actually the first thing they did was drop the parentheses because there's nothing to distribute. And then we take 2x squared minus x squared is going to be x squared. Then we have 3x, and then we have negative 5 plus 1 is negative 4. So that is getting to that expression. So that is addition. There's nothing more to add there. When we get over here to g of x, subtraction, it says f of x minus g of x. So you have to do it in that order. So we took f of x and we subtracted g of x. And then once here it is, we distributed everything by that negative 1. So once we get to that point, then we can go ahead and combine like terms. You got negative 2x squared minus x squared, so that would be that negative 3x squared. You have 3x again, and then now before we had a minus in there, but now we have 5 plus 1, so we have 6. So that is what it looks like when we subtract g of x from f of x. And let's see here to do another example. This comes from our assignment today. But we have f of x is 2x, and then g of x is negative 4x plus 5. So it asks us to add those together. So we have, again, it's going to be f of x plus g of x. So I have 2x plus, in this case, negative 4x plus 5, which is 2x minus 4x plus 5, or in this case, simplifies to negative 2x plus 5. Okay, that's a lot of steps to show you what's going on there for a pretty simple problem, but just making sure we understand the process. And then subtracting, again, this would be my f of x minus g of x. So f of x is going to be 2x minus, and then my g of x is negative 4x plus 5. Distributing that negative sign, right? Everything's going to change signs. And then I have 2x plus 4x is 6x minus 5. So there's the end result. 2 more examples for us when it comes to that adding and subtracting in the functions. When we multiply and divide, multiplication can sometimes get a little bit hectic because we end up doing some form of FOIL or distributive property depending on how big our functions are. But again, f of g of x is f times g of x is saying f times g of x. So f times g of x. F of x times g of x. So here is f of x given to us in the question, g of x given to us in the question, and then we do the distributive property. So they multiplied negative x times all of this, then they multiplied positive 5 times all of this, and then now when they do the distributive property, they had negative x to the third, negative x times negative 2x's is going to be 2x squared. So let's see, which ones have I accounted for? This one, and then I have negative 3x, this one, and then 5 times 4x squared is going to be 20. 5 times negative 2x is going to be negative 10x, and then 5 times 3 is going to be 15, and then they combine like terms and they come up with this answer. Okay, that is what the two functions look like when they are multiplied together. Division, well, they took f of x and they divided it by g of x, and I do not believe there's anything further to do there. Are we able to factor? We cannot factor this trinomial any farther. And then I guess this is the one caveat that they want to make sure that you know that x cannot equal 5, because if x was 5, the denominator would be 0 and it would be undefined. So that's a limitation. We have a constraint that we have to make sure we're aware of. All right, so multiplying, and I'll give you a second to do this, but they're asking us to multiply f of x times g of x, and they're asking us to divide f of x by g of x. So take a moment. Okay, so here I have f of x times g of x. So f of x times g of x, I use my distributive property to distribute these into the other polynomial, distribute one polynomial into the other, FOIL possibly, and I came up with negative x cubed minus x squared plus x plus 1. So that is when I multiply f times g. Now when I divide, I have f divided by g of x. So I notice here I've almost got a perfect difference of squares. So if I factor out a negative 1 from the numerator, I have x squared minus 1, and I can factor that. So I have that negative 1 factored out, and then x squared minus 1 becomes x plus 1, x minus 1. And now this can be simplified. I can simplify that, and my answer is actually negative x plus 1, because I went ahead and multiplied this by the negative again. One thing to remember, though, that x cannot equal negative 1. And I say that because if we have to remember that x cannot equal negative 1, because if negative 1 was input right here, this would be 0. So we want to make sure that we do have that caveat, that constraint identified. Now, that is adding, subtracting, multiplying, and dividing functions. Now here, when they talk about this, it says, suppose f and g are functions such that the range of g is a subset of the domain of f. Then the composition function f of g can be described as f of g of x. And just think about this function notation. If I have this, that means, and then I do this, that means whatever is in my function, wherever there's an x, I want to put in a 4. Well, this notation right here says, hey, wherever there's a x, I'm actually going to put in all of g of x. And that's what that is. So f of g of x. We're going to input g of x for x values. So here, being able to understand that, f of g of x, f of g of x, f of g of x, f of g of x. So evaluate g of x first. So f of g of 4. F of g of 4 is equal to f of 1. Or 12. F of, let me see here, f of g of 4. So f of g of x. So we're going to put g4 into my f of x, right? So when I put 4 in here, I get out a 1. So it would actually be, this is the same thing. G of 4 is actually 1. So f of 1 is 12. Whew, that's tough. Okay, so they're saying, using this information, f of g of x. This is g of x, so g of 5, right? So f of g of 5. When I put 5 into g, I get out a 0. So technically this is f of 0. And f of 0 is 13. Here, g 13. F of g of 13 is going to be 9, so f of 9 is actually going to be 7. When I put 9 into f, I get 7 out. And then here, g of 12. G of 12, g of 12, the output is a 10. So f of 10 is going to be, when I put 10 into the function f, I get out an 11. So that is how we're trying to read these and understand what's going on. So just understanding, this is probably one of the more challenging elements for some people. Just knowing, what does that mean? And if I were to write it out, maybe if we have another equation in a second here, but stating the domain and the range, understanding what is the domain, the domain f of g of x, the domain of the x coordinates of the composed function is the domain 4, 5, 12, and 13. Four, 5, 12, and 13, because that was the input values. The range of the y-coordinates of the composed function, the range is going to be 7, 11, 12, 13. The output, when I plugged those values in, I got out that. We'll do a handful of these in class to make sure that we understand what's going on. Tables are a little bit more difficult probably than the composing of the functions. So here, say f of g of x. So wherever I have x, I'm going to plug in g of x. So f of x is actually equal to 2x minus 5. So wherever there is an x, I am going to put in g of x. G of x is 3x, so I have 2 times 3x minus 5. So f of g of x is equal to 6x minus 5. That's what they're hinting at here. And this was f of g of x. Now, g of f of x is going to be equal to, let's see here, we have g of x. Thinking about that is g of x is 3x. Then I'm going to take and put f of x, so that would be the same thing as f of x. So I would have 3 times 2x minus 5, 6x minus 15. Okay, so that's what they're doing. They're inputting one function into the other function. That is what we're looking at. Let me see here. I've given you the domain and ranges here on these, but again, check. Given f of x and g of x, find f of g of x and g of f of x. Again, so f of g of x is going to be, we take f and we put g of x in it. So I have f of g of x is equal to negative 2x cubed minus x plus 1. I would have negative 2x cubed plus x plus 1. And that would be my f of g of x. For g of f of x, again, I'm going to take g, and wherever there's an x, I'm going to put in the function f of x. So g of f of x is going to be something along the lines of 2, and then x is going to be negative x plus 1 is f of x cubed minus negative x plus 1. And that's again, I'm taking f of x and I'm plugging it in here and here. Let's see, so you have to do this thing first. You have to cube it first. And then I'm going to take and add that. So I simplified that. Cubing that function, it's a little bit, see here I have negative x plus 1 times negative x plus 1 times negative x plus 1. So this would be my first option, negative x times negative x plus 1 plus 1 times negative x plus 1. And that is going to equal x squared minus x plus 1, or x squared minus 2x plus 1. And then multiplying again, times minus x plus 1, which is going to negative x times x squared minus 2x plus 1, and then plus 1, right, times x squared minus 2x plus 1. Using your distributive property here, we have negative x cubed plus 2x squared minus x plus x squared minus 2x plus 1. This simplifies to negative 3x. This simplifies to 3x squared. So I have negative x cubed plus 3x squared minus 3x plus 1. So a little bit more work there, but it's definitely something we can handle. So there you go. Now, the movie theater charges $8.50 for each of the X tickets sold, and the manager wants to determine how much the movie theater gets to keep the ticket sales, how much gets to keep of the ticket sales if they have to give the studio 75% of the money earned on the ticket sales. If the amount they keep on each ticket sale is KX, find the composition, which composition represents the total amount of money that the theater gets to keep. Uno momento, por favor. You know, I had to think about it, and I remembered I did something. It seemed like something was wrong. We forgot, or I forgot, I have this value over here still. I had to multiply that whole thing times 2, and then I still need to add in plus x minus 1. So that actually becomes negative 2x cubed plus 6x squared minus 5x, right? Because this would be minus 6x plus 1x. And then plus 1, because I would have 2 times 1, which is 2 minus 1. So that's actually the answer. And it's frustrating sometimes when we do maths. We just accomplished something, and we did everything that we were expected to do, and we found x. But they wanted to know the actual value, not x. And we sometimes lose track when we get into all this computation that, oh, there was some more stuff I needed to add into that. So there we go. That's the actual answer. So my apologies. Let's let's see if we look here. What do we, now going back to this word problem. If the amount they keep of ticket sales is KX, which composition represents the total amount of money the theater gets to keep? Okay, so you have a function of ticket prices, and then the function of the portion of the ticket prices they keep. So we pay $8.50. It seems like $800 anymore when you go to the movies. But we have this function of $8.50 per ticket sold. And then we have the amount that they get to keep, which is that, we'll just say K for keep, right? Is equal to 0.25 each ticket sold, because they have to give the studio 75%. So they get to keep 25%, which is the same thing as 0.25 decimal. So there we go. That's one way to calculate this problem. Now, which composition represents the total amount of money the theater gets? The theater gets to keep some portion of the movie tickets. Some portion of the movie tickets. Possibly. So if we take K of X, 0.25, and wherever we plug in X, we use the entire 8.50X. And then when we multiply that out, I think K of F of X should equal 2.125, and then we still have the X. And that should hopefully get us where we want to be. So with that, we're going to do some of these function operations. We'll do a handful of these word problems. The big goal is making sure that we understand adding, subtracting, multiplying, dividing, and then that f of, or the function of another function, being able to plug g of x in for f of x. And that's what we'll do here.